Hello everyone, so in this video I am going to talk about atoms, which is part of modern physics. So I have categorized previous year's questions as problem type. So if you watch this video till end, you have the idea about different types of numericals can be asked in JEE Mains 2025. Now let us see who will get benefited from this video. So you know basics and your NCERT level knowledge is fine and you have done some formal coaching, but you are struggling with the numerical part, so this video is for you. Now how you should watch this video? So first of all, you have to revise the short notes which you have prepared for this particular chapter. Then while watching the video, if you come across any new information, write down that information in your notes. And whenever I discuss an illustration, you have to solve the question on your own, and suppose if you are not able to solve the question, then you can see the solution. Now let us see the weightage. So around one question can be asked from this chapter, and usually the question difficulty is not that high, so it is one like easy question we can say from this chapter. And if you look at the syllabus, we have alpha particle scattering experiment, then Rutherford model hai, Bohr's model is there, then energy level, then hydrogen spectrum, which you have already studied in chemistry. And let us look at the mind map. So different types of models are there, and then we should know, like we have to study Bohr's model in detail, and we should know what is the relation of these different physical quantities in terms of the principal quantum number and the atomic number of the nucleus. And we should also like do practice for the spectral series, right? And what are the hypothetical models of atoms which can be asked in JEE Mains. So the very first problem type is based on distance of closest approach, right? So what we have given in this kind of a question, suppose there is a charged particle and there is a heavy nucleus, and we have given some kinetic energy to this charged particle, and its line of motion is passing through the center of the nucleus. So it has certain kinetic energy, and after some time at certain minimum distance from the nucleus, the kinetic energy will become zero for a moment, right? Now this distance is known as the distance of closest approach, right? This is known as R min. Okay, so let us see the typical question which can be asked from this. So in a alpha particle scattering experiment, distance of closest approach for alpha particle is 4.5 into 10 raised per minus 14 meter. If the target nucleus has an atomic number 80, and then the maximum value of alpha particle is approximately, right? So we have given alpha particle and it has some initial kinetic energy. Let me take its velocity to be v, and here we have a nucleus with atomic number 80, right? So we can say the charge on the alpha particle will be 2 times the charge on the electron. Well, positive, it will be positive charge, right? And the charge on the nucleus will be 80 times E. So when it is at minimum separation from the nucleus, where the velocity becomes 0, the distance is given as R minimum. R min is given to us, and R min is 4.5 into 10 raised per minus 14 meter. Q1 and Q2 are given. So here what we have to do, we have to apply energy conservation. So what is happening here, the kinetic energy is decreasing and the electrostatic potential energy of the system is increasing. So what we can say, loss in kinetic energy will be equals to gain in electrostatic potential energy. So what is the loss? The entire kinetic energy has been lost, so half mv square is equals to, and the gain in and the kinetic energy here will be 0. So gain in electrostatic potential energy, you must have seen this formula. There are two charges, Q1 and Q2, and they are separated at a distance r. Then the potential energy, electrostatic potential energy, will be given as K Q1 Q2 by R. So we're going to use this formula, and when and we have assumed initial separation between the nucleus and the alpha particle is quite large, so the potential energy will be nearly 0. So it can be written as K Q1 Q2 divided by R min, and we have to find V. So V will be square root of 2k q1 q2 divided by m times r min. Now if you substitute the values, so v equals to root of 2 times 9 into 10 raised to power 9. q1 times q2 will be 160, and e square is 1.6 square times 10 raised to power minus 38 by mass is given as 6.72 into 10 raised to power minus 27, that is given in the question for the alpha particle, and the minimum distance is 4.5 into 10 raised to power minus 14, right? So the calculation in this particular problem is tedious, but somehow if you are able to find the answer, it comes out to be close to 156 into 10 raised to power 5 meters per second, right? So the fill in, if we have to fill the blank, and it comes out to be 156, right? Now let us see another problem. An alpha particle with kinetic energy 10 mega electron volt is heading towards the stationary point nucleus of atomic number 50. Calculate the distance of minimum approach or closest approach. So this is the alpha particle, its kinetic energy is given. So K initial is given as 10 mega electron volt, and this is the nucleus which is having a atomic number 50. So again we're going to use the same concept, loss in kinetic energy equals to gain in electrostatic potential energy. So K initial should be equals to K times q1 q2 divided by r min. So this minimum distance we have to calculate, so r min will be k q1 q2 divided by k initial. Now what is the kinetic energy in SI units? So it will be 10 mega electron volt, and 1 electron volt is 1.6 into 10 raised to power minus 19 joules. So it can be written as 9 into 10 raised to power 9. Charge on the alpha particle will be 2 times E, and charge on the nucleus is 50 times E. So that will be E times 1.6 into 10 raised to power minus 19 divided by kinetic energy, which is 10 mega is 10 raised to power 6, and electron volt, so 1 E. So this E will get cancelled out. So let us simplify this. So we got 144 times, so 9 times 16 will be 144, and then we have 10, then 10 raised to power 9 minus 19 plus minus 6. So this comes out to be 144 times 10 raised to power minus 6 minus 15, or we can write this as 14.4 into 10 raised to power minus 14 meters, right? So that should be the minimum distance between the alpha particle and the nucleus. Okay, now the next problem type is based on impact parameter. So first we should know what is impact parameter. Let us understand. Suppose this is a heavy nucleus, and we are assuming this nucleus is not shifting, it is not moving anywhere, it will remain at rest. And there is an alpha particle, and this is the line of motion of the alpha particle. And there is if I consider a line which is passing through, which is parallel to the line of motion, and it is passing through the center of the nucleus, the distance between these two lines is known as impact parameter. If the impact parameter is B, and the initial kinetic energy of the alpha particle is Ki, then this theta is known as the angle of scattering. Due to the strong electrostatic repulsion, the alpha particle will be deviated from its original path. So the deviation produced in the alpha particle is known as the scattering angle or angle of scattering, and which is theta. So you should remember this relation. So impact parameter is K, which is K is 9 into 10 to the 9. Q1, Q2. Q1 is the charge on alpha particle, Q2 is the charge on the nucleus, upon 2 times Ki, which is the initial kinetic energy of the alpha particle, times cot theta by 2. Now let us see the application of this formula. So the impact parameter is K Q1 Q2 divided by 2 times Ki cot theta by 2. So we have given root d1 and root d2 are the impact parameters corresponding to the scattering angle 60 degrees and 90 degrees respectively when an alpha particle is approaching a gold nucleus. for d1 equals to x times d2, the value of x is. So basically we have to compare the impact parameter. So we can say b1 by b2 will be equals to cot theta 1 by 2 upon cot theta 2 by 2, because this factor will remain same for both the cases. And b1 is given as root times d1 and b2 is given as root times d2, and theta 1 is 60 degrees, so that will be cot 30, and theta 2 is 90, so that will be cot 45, and cot 30 is root 3, and cot 45 is 1. Now let us square this. So d1 comes out to be 3 times d2, so x is nothing but 3, right? So now let us see the next problem type, and it is based on Bohr's postulates. Yes, so let us see the first question. The radius of third stationary orbit of electron for Bohr's atom is r, the radius of fourth stationary orbit. So here you should remember this formula. The radius of nth orbit will be 0.529 angstrom times n square by z, where n is the principal quantum number and z is the atomic number of the atom. So sometimes we have given, so here we have given, yeah, so nothing is mentioned like which atom they're talking about. It can be hydrogen, it can be helium plus, it can be lithium 2 plus, right? So this is given to us. So this relation we have to remember. So here what you have to use, so Rn will be proportional to n square. So the radius of third stationary orbit of electron for Bohr's atom is r. So that is given as r. R is some 0.529 angstrom times third, right? So that will be 3 square by z, and we have to find the radius of fourth stationary orbit. So let us say r4 will be 0.529 angstrom times 4 square by z. Now let us take the ratio of 1 and 2. So 2 by 1 will be r4 upon capital R will be 9 by 16. So r4 comes out to be 9 by 16 times capital R. Okay, so here usually the questions will be based on proportionality. So option 4 is the right answer. Right, so let us see the next question. The ratio of the magnitude of kinetic energy to the potential energy of an electron in the fifth excited state of the hydrogen atom. So first we should know what is the formula of kinetic energy and the potential energy. So potential energy is given as minus 27.2 z square by n square electron volt, where z is the atomic number of the atom. In this case we have given hydrogen, this z will be 1. So z is 1 in this case, right? And the kinetic energy will be 13.6 z square by n square times electron volt, right? Again z is equals to 1. And we have to find the ratio of the magnitude of kinetic energy and the potential energy. So if we take the ratio for the fifth excited state, this n value is also same for u and k. So u magnitude u divided by magnitude of k will be 27.2 divided by 13.6, which comes out to be 2 ratio 1. Sorry, we have to find the ratio of kinetic energy to the potential energy, so that will be 1 ratio 2. So 1 by 2 is the answer. So let us see the next question. An electron revolving in nth Bohr's orbit has magnetic moment mu n if mu n is proportional to n raised to power x, the value of x is, right? So magnetic moment. So what is the relation between magnetic moment and the angular momentum for the charged particle which is revolving? Just remember this: magnetic moment upon angular momentum, this will be q divided by 2m, right? So this relation you can remember, and since it's an electron, there has to be a negative sign also, but we don't have to worry about the negative sign because it is not given in the question. So we can say the magnitude of mu n by the magnitude of ln will be q by 2m, where q will be e by 2m. And we know that like as per the Bohr's second postulate, the angular momentum is conserved. So ln is given as nh upon 2 pi. So we have to use this relation. So mu n will be E by 2m times nh upon 2 pi, right? And for nth orbit they are talking about. So from this we can say mu n is proportional to n raised to power 1. So the answer will be x will be 1 only. So option 2 is the right answer. Right, so let's see the next question. According to the Bohr's theory, the moment of momentum of the electron is nothing but the angular momentum, right? This is angular momentum. And angular momentum is conserved of electron revolving in fourth orbit. So angular momentum is given as nh by 2 pi, and for fourth orbit n will be 4, so L4 will be 4h upon 2 pi, which will be 2h upon pi. So option 4 is the right answer. Now let us see the next question. An electron rotates in a circle around a nucleus having a positive charge Ze. Correct relation between the total energy of the electron to the potential energy. So the mechanical energy is given as minus 13.6 Z square by n square electron volt, and the potential energy is given as minus 27.2 Z square by n squared electron volt. So we have to find the correct relation between these two. So we can clearly see that potential energy is 2 times the mechanical energy. So option 2 is the right answer. Next question. The angular momentum of an electron in hydrogen atom is proportional to, so again angular momentum is nh upon 2 pi by the second postulate. So it is directly proportional to n, and we have to find the relation with the radius. And we know that radius of the nth orbit is proportional to n square by z, and for hydrogen z is 1. So we can say Rn is proportional to n square, and n will be proportional to square root of Rn. So we can say Ln will be proportional to n, or we can say Ln will be proportional to root Rn. So it will be yes, the option 2 is the right answer. Yes, so now let us see the next question. The radius of a certain orbit of hydrogen atom is 8.48 angstrom. If the energy of the electron in this orbit is E by x, then what is the value of x? So we have to find the energy, and we have given the radius. And we know that Rn is 0.529 angstrom times n square by z. And it's in a hydrogen atom, so this will be just n square, right? Z will be 1. And this is given as 8.48 angstrom. So n square will be 8.48 divided by 0.529, and this will be nearly equals to 16. So n comes out to be 4. Now we got the principal quantum number, and we have to find the energy. And so we know that the mechanical energy is given as minus of 13.6 times z square by n square. So z will be 1, and n for fourth orbit will be 4 only, right? So it comes out to be minus 13.6 divided by 16. And E is the energy of the electron in the ground state. Okay. So energy, okay, let me write this as E4, right? E4. So energy of the electron in ground state is given as E, which is minus 13.6 electron volt. So this is E by 16. So the energy in the fourth orbit is E by 16. So we can say the value of x will be 16, right? So 16 is the answer. Now let us see the next problem type, and it is based on spectral series. So let us see the first question. If the wavelength of first member of Lyman series of hydrogen is lambda, the wavelength of the second member will be. So for Lyman, we know that 1 by lambda will be equals to Rydberg's constant times 1 minus 1 by n square, where n can be 2, 3, 4, so on and so forth. Now for the first member, n is equals to 2, and for the second member, n will be equals to 3. So what we can say, 1 by lambda for the first member will be R1 minus 1 by 4. And for the second member, let me call the wavelength as lambda 2 is equals to R times 1 minus 1 by 3 square, which is 9. So this comes out to be 8 by 9 times R, and this comes out to be 3 by 4 times R. And we have to find lambda 2. So if this equation is 1, this equation is 2. So if we divide 1 by 2, we'll get lambda 2 by lambda is equals to 3 by 4 times 9 by 8. So this comes out to be 27 by 32. So lambda 2 will be 27 by 32 times lambda. So option 1 is the right answer. Let us see the next question. The minimum energy required by the hydrogen atom in ground state to emit radiation in Balmer series is nearly. So what do you mean by Balmer series? Let me show the energy level first. Suppose this is the ground state, then this is the first excited state, this is the second, and this is third, like this, right? So n is equals to 1, n is equals to 2, here n is equals to 3, n equals to 4. So to emit radiation in the Balmer series, the electron from the higher energy level jumps to the first excited state. So you can say this will be the first line from 3 to 2, and the second line will be from 4 to 2. Right, so the minimum energy required by the hydrogen atom in ground state to emit radiation. So we have to the minimum. So basically, you have to excite the electron from ground state to the second excited state. Only then it will be able to emit radiation in Balmer series. So that should be the minimum energy, right? So the energy gap between the ground state and the first excited state will be the answer. So let us find that. So E3 minus E1. So that will be 13.6. I'm using this formula, minus 13.6 Z square by N square electron volt. So that is the energy of particular um, state, right? So 13.6 times 1 minus 1 by 9 electron volt. So this comes out to be 13.6 times 8 by 9, and this is 12.1 electron volt. So option 4 is the right answer. Let us see next question. If Rydberg's constant is R, the longest wavelength of radiation in Paschen series. So in Paschen series, 1 by lambda is equals to R times 1 minus 1 by 3 square, right? Sorry, not 1 by 3 square. Let me correct this. In Paschen series, the electron jumps from a higher energy level to n equals to 3. So that will be 3 square, and this will be n square, where n can be 4, 5, 6, so on and so forth. And we are talking about, they have given, they are saying that the longest wavelength of radiation. So when we have the longest wavelength? So wavelength will be longest if the energy gap is least. So for the very first line of Paschen series, we'll get the longest wavelength. So when the electron jumps from 4 to 3, then lambda will be maximum. And when the electron jumps from infinity to 3, then lambda will be minimum. Right, so let us simplify this. So we have to find the longest wavelength. So we are going to consider this transition. So 1 by lambda is equals to R times 1 by 9 minus 1 by 16. So that comes out to be R times 7 by 144. So lambda will be 144 upon 7R. So if we compare this, it is given as alpha time upon 7R. So alpha comes out to be 144. So 144 is the answer of this question. Right, so let us see the next question. Hydrogen atom is bombarded with electron accelerated to the potential of V. So we have accelerated electron with the potential difference V. So the kinetic energy acquired by the electron will be E times V, which causes excitation of the hydrogen atom. If the experiment is being formed at T equals to 0 Kelvin, the minimum potential difference needed to observe any Balmer series line in the emission spectra. So in case of a Balmer, electron jumps from a higher energy level to the first excited state. So this is n equals to 2, n equals to 1, n equals to 3, n equals to 4. So that is the first line of the Balmer series. This is the second line of the Balmer series. So if we want to excite an electron which is in the ground state so that it can show the line in the Balmer series, so you should give at least that much amount of the energy, which is nothing but E3 minus E1. So it comes out to be 13.6. 1 minus 1 by 9. So 13.6 times 8 by 9, so which comes out to be 12.1 electron volt. And this is given as alpha by 10. So it is saying the minimum potential. So if we have a electron which is having an energy E times V, and when it strikes with the hydrogen atom, it loses its energy completely, and that energy will be acquired by the hydrogen atom, and then it will so the electron will gain energy and it will jumps to the first excited state. So we can say the energy will be E times alpha by 10, and from this alpha comes out to be 121, right? So 121 is the answer of this question. Now let us see the next question. The shortest wavelength of spectral line in Lyman series of hydrogen atom is 915 angstrom, and the longest wavelength of spectral line in Balmer series. So shortest wavelength in Lyman series is given, and we have to find the longest wavelength in Balmer series. Right, so when do we have shortest wavelength? When the energy gap is maximum. So in case of Lyman, the shortest wavelength will come when the transition happens from infinity to 1. And the longest wavelength will get the longest wavelength when the transition happens when the gap is minimum, right? In that case, the lambda will be maximum. So the longest wavelength in case of a Balmer will be from 3 to 2, right? So first let me call this wavelength as lambda 1 and this as lambda 2. So we have to find lambda 2. So 1 by lambda 1 is r times 1 by 1 square minus 1 by infinity square, which comes out to be r. And 1 by lambda 2 will be r times 1 by 2 square minus 1 by 3 square. So that will be r 1 by 4 minus 1 by 9, so which comes out to be 5 r by 36. And if we substitute lambda value in the first equation, r comes out to be 1 upon 915 angstrom. So now substitute r value in the second equation. So 1 by lambda 2 will be 5 by 36 times 1 by 915 angstrom. So lambda 2 comes out to be 183 times 36 angstrom. So if we simplify this, it comes out to be 6588 angstrom. So 6588 angstrom will be the answer of this question. Let us see the next question. The ratio of the shortest Balmer series, shortest wavelength of Balmer series to the shortest wavelength of Lyman. So shortest wavelength in case of Balmer, shortest wavelength will be when the energy gap is the maximum. So in Balmer it will be from infinity to 2, and in Lyman it will be from infinity to 1. Okay, so let us say this wavelength is lambda 1, this wavelength is lambda 2. So 1 by lambda 1 is equals to r times 1 by 2 square minus 1 by infinity square. So that comes out to be r by 4. So 1 by lambda 1 is r by 4, and 1 by lambda 2 will be r times 1 by 1 square minus 1 by infinity square. So that comes out to be 1 by lambda 2 is r. And we have to find the ratio. So if I divide second equation by the first equation, we'll get lambda 1 by lambda 2 r times 4 by r. So which will be 4:1. So option 1 is the right answer. Now let us see the next problem type, and it is based on the transition of the electron. A particular hydrogen-like ion emits the radiation of frequency 3 into 10 raised to 15 Hertz when it makes a transition from 2 to 1. The frequency of the radiation emitted in the transition from 3 to 1 is x by 9 into 10 raised to the 15 hertz, and we have to find the value of x, right? So we know that the photon which is being emitted when the electron transit from one state to another state will be, so we can say h times nu will be, you can say like the difference in the energy, right, delta E. So we can say h times 3 into 10 raised to the power 15 will be 13.6, 1 by 1 square minus 1 by 2 square electron volt, right? Similarly, we can apply the same equation for the second transition. So h times x by 9 into 10 raised to the power 15 in hertz equals to 13.6. So 1 by 1 square minus 1 by 3 square. Now we can take the ratios. Let me call this second equation. This is first equation. So 2 divided by 1 will give us x by 9 times 1 by 3 equals to, and this will be 1 minus 1 by 9 divided by 1 minus 1 by 4. So it will be 8 by 9 times 4 by 3. So, so 9 and 3 will get cancelled out. So x comes out to be 32, right? So 32 is the answer of this question. That is the next question. When the hydrogen atom going from 2 to 1 emits a photon, its recoil speed is x by 5 meters per second. We have to find the value of x, right? So electron is coming down, it is losing energy from, and it is coming down from the first excited state to the ground state, and it releases a photon, right? Which is having energy which is different of these two energy levels, E2 minus E1. And this photon must be having the momentum. So the linear momentum of the photon will be E by C, right? So that is the linear momentum. And if you apply energy momentum conservation, so the momentum, for example, if this is the hydrogen atom and that is the photon, and this is the linear momentum of the photon, and this is the linear momentum of the atom. So by momentum conservation, the vector addition of these two momenta should be 0, right? So I'm assuming that the atom was initially at rest. So we can say the magnitude of linear momentum of hydrogen atom is equals to the magnitude of linear momentum of photon. And we know that for a particle, the linear momentum is given as mass times the velocity, and for the photon it is delta E by C. So from this, the speed will be delta E divided by m times C. So let us put the values. So delta E can be written as, so we can, so 13.6, and it is a hydrogen atom. So it will be 1 by 1 square minus 1 by 2 square, and it is in electron volt. And we have to find answer in SI units. So you have to multiply this with 1.6 into 10 raised to the power minus 19 by mass, which is 1.6 into 10 raised to the power minus 27, which is given in the question, and the speed of light in vacuum, 3 into 10 raised to the power 8. Let us simplify this. So 1.6 will get cancelled out, and this is 3. So this will give us 4. Okay, let me simplify this further. Okay. So this can be written as 13.6 times 1 minus 1 by 4, that will be 3 by 4, times 1 by 3 times 10 raised to the power minus 19 plus 27 minus 8. So this 3 will get cancelled out. So this comes out to be 3.4. 3.4. Yeah. So 3.4 times 10 raised to the power 0. So velocity will be 3.4 meters per second, and we have given this velocity as x by 5, so which will be 3.4 times 5, and it comes out to be 17. So x will be 17 in this question, Right, so let us see the next question. An electron of hydrogen atom on an excited state is having an energy minus 0.85 electron volt, the maximum number of allowed transition to the lower energy level. Okay, so what we have to suppose if the electron is in nth orbital, let us say. So how many possible transitions are there? It will be n times n minus 1 by 2. So basically we have to figure out, we have to find the value of n, and then we can use this relation, we can use this formula to find the answer. How many possible transitions will be there? So En is given as minus 0.85 electron volt. So minus 0.85 electron volt can be written as minus 13.6 electron volt times 1 by n square. So n square will be 13.6 divided by 0.85, so which nearly equals to 16. So n comes out to be 4. Since n is 4, now let us put the value of n in this equation, in this formula. So 4 times 4 minus 1 by 2, so that will be 6. So 6 is the answer of this question. Right, so let us see the next question. A hydrogen atom changes its state from 3 to 2 due to recoil. The percentage change in the wavelength of emitted light is approximately 10 raised to power minus n. The value of n is. So what do you mean by the percentage change in the wavelength? For example, if we assume that there is no recoiling, right? In case of no recoiling, we can say whatever will be the loss in the energy, and that will be that is this nothing but the energy of the photon. So we can say 13.6 1 by 2 square minus 1 by 3 square, so that will be 13.6 times 1 by 4 minus 1 by 9, and 13.6 times 5 by 36. Okay, and this comes out to be 1.89 electron volt. Got it? Yes, 1.89 electron volt. Now so if there is no recoiling, then we can say the lambda hc by lambda will be nothing but delta E. So lambda comes out to be hc by delta E. Okay, we can use this. But suppose if we consider recoiling, so in that case, some of this energy will also go into the kinetic energy of the atom. And we know that the linear momentum will be conserved. So we can say the linear momentum of the photon and the linear momentum of the atom, it should be 0, right? So because we are assuming that the atom was initially at rest. So if that is the case, the linear momentum of the atom will be nothing but the energy of the photon divided by the speed of light in vacuum. It will be same as the momentum of the photon. So here we can see delta E will be half mass of the atom times the like, or I can we can also write this in terms of the linear momentum. Linear momentum. So this will be half times p square by 2m, where p is the momentum of the atom, plus, so this is the kinetic energy of the atom, and then the energy of the photon. Energy of the photon will be hc by lambda prime, right? That is the energy. And this delta is nothing but 1.89 electron volt. And delta E can also be written as hc by lambda. So this 2 won't be there. So 1 by 2m times linear momentum of the atom will be energy. So that will be, so in this case the energy, linear momentum of the atom, so this energy will be hc by lambda prime, right? Or you can say h by lambda prime. So let us substitute this value in this equation. So it will be h square by lambda prime square plus hc by lambda prime. Now if I multiply, okay, so here we have delta E, no? Let me keep it as delta E only. So delta E times lambda prime square, then minus hc times lambda prime minus h square by 2m equals to 0. Now we got a quadratic in lambda prime. Now we have to solve this quadratic. So let me write it here. So delta E so lambda prime will be what? It will be minus b plus minus root b square, which will be h square c square plus 4 times ac, and a is delta E, c is h square by 2m. Okay, now what we can do, let us multiply this term with c square and divide by c square and divide it by 2 times a, which is delta E. So this hc square will be common. So we can say hc times 1 plus minus root of 1 plus 4 delta E by 2 mc square divided by 2 times delta E. Now hc by delta E, if you look at this relation, hc by delta E is lambda. So that will be lambda by 2. So 1, and I'm ignoring the negative sign, so it should be 1 plus 2 delta E divided by 2 mc square raised to power 1 by 2. Now if you look at delta E and mc square, now this 2 delta E will be very small in comparison to mc square, which you can check. So we can use binomial approximation. So this can be written as 1 times 1 plus 1 by 2 times 2 delta E by mc square. So we can write this as lambda by 2, 1 plus 1 plus 1 by 2 times 2 delta E divided by mc square. Okay, so let us simplify this further. So lambda times 1 plus delta E by 2 mc square is equals to lambda prime. Now from this lambda prime by lambda minus 1 comes out to be delta E divided by 2 mc square. So left hand side is what? It is lambda prime minus lambda upon lambda, which is delta lambda by lambda is equals to delta E upon 2 mc square. And we have to find the value of n, so the percentage change. So we have to find the percentage change. So for that, let us multiply this with 100. So 100 times delta lambda by lambda is equals to delta E divided by 2 mc square times 100. Let us put the values. So delta E is 1.89 into, it is in electron volts, so 1.6 into 10 raised to power minus 19 times 10 raised to power 2 divided by 2 times mass of the hydrogen atom is given as 1.6 into 10 raised to power minus 27. So 1.6 into 10 raised to power minus 27, and c square will be 9 into 10 raised to power 16. So let us simplify this. So that will be 0.21. 1.6 will get cancelled out. So this will be 0.105 times 10 raised to power minus 19 plus 2 plus 27 minus 16. So which comes out to be 27. Yeah, so 20 minus 8, 10 minus 6. So that will be 0.105 into 10 raised to power minus 6. Or I can write this as 1.05 into 10 raised to power minus 7. And if you look at the answer given, so we have given that the percentage change in the wavelength is 1 into 10 raised to power minus n. So we can say it is nearly equals to 1 into 10 raised to power minus 7. So n comes out to be 7, right? So this is not easy. This question has lots of calculation. Now let us see the next question. A hydrogen atom in ground state is given an energy of 10.2 electron volt. How many spectral lines will be emitted due to the transition of the electron? So we have given electron in the ground state which is having energy minus 13.6 electron volt, right? And we have given it 10.2 electron volt. So the energy of the new state will be minus 13.6 plus 10.2, which will be minus 3.4 electron volt. And this will be equals to minus 13.6 by n square. So n square comes out to be 13.6 by 3.4. So that comes out to be 4. So n should be equals to 2. So n is 2, and we have to find how many spectral lines will be there, and what is the formula for that? N times n minus 1 by 2. So let us put n equals to 2 in this equation. So 2 times 2 minus 1 by 2, so it comes out to be 1. So option 4 is the right answer. Right, so let us see the next question. In Frank Hertz's experiment, the first dip in the current voltage graph for the hydrogen is observed at 10.2 volts. The wavelength of the light emitted by the hydrogen atom when excited to the first excitation level in nanometer. So what it says, so what happens in Frank Hertz's experiment, so we have a hydrogen gas and then we accelerate electrons with a potential, with certain potential, and when these electrons bombard with the hydrogen atom, it loses energy, and that energy will be acquired by the hydrogen atom, and the electron which is in the lower state will jump to the higher state. Now in this case, the energy of the electron is 10.2 electron volt. So the hydrogen atom has acquired that energy. So that's why the electron which is reaching the collector plate will not able to reach there. So that's why the current in the circuit will dip. So we can say the transition from the ground state to the excited state, and this energy gap will be 10.2 electron volt. So if this is minus 13.6 electron volt, then the energy E will be 10.2 plus minus 13.6. So it comes out to be minus 3.4 electron volt, right? And what is the value of n? So it will be minus 13.6 divided by n square. So n comes out to be 2, right? So n comes out to be 2. So they're talking about the wavelength. So we can say hc by lambda will be 13.6. Achha, that is also given to us, right? If you look at the data, they have clearly mentioned hc is 1245 electron volt nanometer. So we can say hc by lambda will be 13.6, 1 minus 1 by 2 square. And this hc is 1245 electron volt nanometer. So 13.6 electron volt, and this will be 3 by 4. Lambda, it will be in nanometer only. So 1245 divided by 13.6 times 4 by 3. Okay, so let us simplify this. So this will be 3.4, and this will give us 415, and if we simplify this 3, it will be, and we have to find the answer in nanometer, so it will be nearly 122 nanometer, right? So lambda comes out to be 122 nanometer in this question. So that is the answer. Okay, right. So now let us see the next problem type, and it is based on the hypothetical Bohr model. And what do we mean by that? So in Bohr's model, what we have seen, the centripetal force, the very first postulate, it talks about the centripetal force will be nothing but the electrostatic attraction between the nucleus and the electron. But in hypothetical Bohr model, that force will be given something else, right? For example, they will say the force is inversely proportional to r cube, but we know that electrostatic attraction is inversely proportional to r square, or they will give some other relation. So the first postulate will change, the remaining two postulates will remain same, right? So let us see some typical question that can be asked. Suppose an electron is attracted towards the origin by the force k by r. Can you see here it is inversely proportional to r. It is not inversely proportional to r square. Where k is constant, r is the distance of the electron from the origin. By applying Bohr's model to the system, the radius of the nth orbit of the electron is found to be Rn and the kinetic energy is Tn. Then which of the following is true? Right, so let us see. So force is given as k by r, and this is nothing but the centripetal force. Let me call this as Rn, right? Rn is the radius of the nth orbit. And the centripetal force can be written as mvn square by Rn. Now from this, mvn square is equals to k, because Rn will get cancelled out. So we can say Vn square is k by m. So Vn comes out to be constant, right? So Vn is constant. So if we want to find Rn, we can use the second postulate, which is the conservation of angular momentum. So Ln, which can be written as mvn Rn, that is nh upon 2 pi. So Vn is constant. So we can say Rn will be, h is constant, 2 pi is constant, Rn will be proportional to n only, right? And the kinetic energy is half mvn square. Since Vn is constant, mass is constant, so kinetic energy is constant. So as kinetic energy is constant, it does not depend upon n. So if you look at the option B, it says kinetic energy is independent of n and Rn is proportional to n. So option B is the right answer. Right, so let us see another question. In the Bohr's model of hydrogen-like atom, the force between the nucleus and the electron is modified as, so can you see again, this is not a typical Coulomb formula. It is E square by 4 pi epsilon naught times 1 by r square plus 1 plus beta by r cube, where beta is a constant. For this atom, the radius of the nth orbit in terms of Bohr's radius is, and Bohr radius is given as epsilon naught times h square by m pi e square. So let us see what we can do. Again, our first postulate will change. Bohr's first postulate will change. So we can say this force is nothing but the centripetal force. So m vn square by rn should be equals to e square upon 4 pi epsilon naught times 1 by rn square plus beta by rn cube, right? So if I multiply throughout by Rn cube, what we'll get? So it will be mvn square equals to e square upon 4 pi epsilon naught. So this will be Rn square. So we are multiplying with Rn cube. So this will be Rn plus beta. Okay, and what is the second postulate of Bohr's second postulate? It is mvn Rn is equals to nh upon 2 pi. And if you take the square of that, we'll get n square h square upon 4 pi square. So if I multiply with m and divide by m on the left hand side, so this is nothing but the square of the angular momentum. So this can be written as n square h square upon 4 pi square times m. Okay, so from this equation 4 pi will get cancelled out, and we have Rn plus beta is equals to n square h square epsilon naught divided by pi m e square. Now what is a naught? What is the Bohr's radius? It is epsilon naught h square upon m pi e square. So this factor is nothing but the Bohr's radius. So it comes out to be n square times the Bohr radius. So Rn will be n square times the Bohr radius minus beta. So that should be the radius of the nth orbit. Let us see the option. Option C is the right answer. Now let us see the next problem type. And here sometimes you will get questions based on some theory. So let us see one of the question. Statement 1 is most of the mass of the atom and all its positive charge are concentrated in a tiny nucleus and the electron revolves around it, and it is Rutherford model. Yes, that is correct. And the second statement says an atom is a spherical cloud of positive charge with electron embedded in it, is a special case of Rutherford model. That is incorrect. This is Thomson's model, right? So statement 1 is correct, but the statement 2 is false. So option 3 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.